When we look at the acoustic damping, which is measuring the responses between the outside and inside microphones, we see a similar trend as before with using the measurement system and without using the measurement system. But once again, if we block those out, you can see there's a clear trend. We do have one anomaly, however, and that's with the 4-group system here. And our primary guess with this is that it's being more affected by the parallel configuration when you're talking about the amount of noise transmitted through the panel. However, we're going to have to run some further tests on that to actually see why this one varies so much from the rest of the trend. And there are some limitations with this experiment. First, we were limited by the amount of power with our computer that we used to analyze the results, because that limits the response speed of the switches. However, this wasn't a negative effect because we still found almost a 14% decrease in or increase in acoustic damping with this limitation. So with a more powerful computer, which is used on the rockets, we would see an increase in our results, which is a positive thing. And some causes that we saw with why the data drastically changed between an all-series configuration as you move towards all-parallel configuration is what we call forward voltage of diodes. So within the circuit, there is a diode, and ideally it would be 0 volts. However, our actual configuration has 1/2 to 1 volt forward voltage, so we have to overcome that in order for the system to work. And usually you'll need 3 to 4 volts for this system to work. And one way to get around that is either to increase it to all series or to increase the speaker output, which we didn't want to do because we wanted to keep the speaker output consistent for all of our tests. And with the measurement system here, the reason that we had such a drastic difference between using the measurement system and without using the measurement system is that the input impedance for this measurement system is very low, meaning it requires charge in order to power it. And when you're in all-series configuration, you have higher voltage but lower charge. And when you move to a more parallel configuration, you have higher charge but lower voltage, which is why we are unable to test in an all-parallel configuration. However, when you're using the all-series configuration as well as the 10 groups, we notice the difference here because there's a small amount of charge that's stored in that system. And when this data recording system extracts some of that charge, it negatively affects the results of the system, which is what we found and was confirmed by our data. And overall, our conclusions were that there is a direct correlation between vibration suppression and acoustic damping. And we saw that that can increase by up to 14%. We also noticed that there was the circuit configuration drastically affects how much our method works, as well as the measurement system with that extraction of the amount of charge that was used in the system. For acknowledgments, I'd like to acknowledge the National Science Foundation as well as the Japan Society for the Promotion of Science for sponsoring my fellowship to do this work this summer, as well as the Japan Aerospace Exploration Agency, specifically the Institute of Space and Astronautical Science for sponsoring this research, my lab mates Yabu-san and Nando-san, as well as my lab mates at USC at the MC Gill Composite Center, and my Japanese lab mates at JAXA. Now I'd like to open the floor for any questions.
Portia, do you have any questions? Well, let me ask you. Oh, good.
I believe you said that you tested this at, was it 280 hertz?
Correct.
So, first of all, why did you choose that? And then second of all, what's the, how do you expect that would translate when, I mean, I presume that there's vibration at all kinds of hertz. Do you expect that these electric devices would be able to damp it across many?
Yes. Well, to answer your first question, we tested at 280 hertz because it was the first natural frequency of that structure, that material, the honeycomb sandwich structure. And we do believe that this method will work across an entire frequency range. However, we've noticed that the magnitude of the first mode is the biggest and often causes the most damage. So we're making the assumption that by it affecting the first mode, that it will affect the consequent mode as well.
I'm curious if you extend this to other materials. Do you think it would also translate those systems?
Yes, I think this method will translate into all systems that are negatively affected by vibrations, because it's not dependent on the material per se, it's dependent on the vibrations and the source of vibrations. So even for this method or this experiment, we were vibrating it through speakers, whereas with the actual rocket, it will be vibrated just from the natural environment from having all that thrust applied. So it can be applied to all materials.
All right, well, let's thank Portia again. Thank you.